Canada, and grew up near London, England, where she received a master's degree in chemistry with industrial experience from the University of Manchester in the UK. Subsequently, she earned her PhD studying diastereoselective olefin dihydroxylations with Professor Steve Davies at the University of Oxford before joining Pfizer at Sandwich in the UK in 2008. After a couple of site moves, she continued working in medicinal chemistry, landing here in Groton in 2017, and is now part of our internal medicine group, where she enables top-notch synthesis to deliver new therapeutics to the clinic. When not at work, Caroline enjoys spending time with her family and gardening. And today, Caroline will share a story with us about optimizing useful synthetic transformations to enable compound delivery on milligram to kilogram scale. And specifically, her talk is entitled Synthetic Challenges of Chiral Alpha Methylated Aryl Acetic Acid Derivatives. And I've seen this, and it's a really nice mix of bench chemistry, flow, and biocatalysis. A little bit of chemistry for everybody. So, Caroline, all you, go ahead and share your slides and take it away.
Thank you so much, Scott. Can you see my slide?
Yeah, looks perfect. Thank you very much.
Great. Yes, so thanks for that introduction, and thank you to all the organizers for inviting me to speak with you today. So as Scott said, the title of my talk is The Synthetic Challenges of Chiral Alpha Methylated Aryl Acetic Acid Derivatives. And really, my talk is taking you through some of the challenges that we face on our medchem programs and how we go about designing syntheses to overcome them. And I'll talk you through some of the teams and the strategies that we use. So I'll just set myself up with the pointer. Okay. So I'll just start by acknowledging the team involved in the chemistry that I'll talk about. We have a series of colleagues in the medchem, our technology line, process and purification really coming together to develop those chemistries for scale-up. I'll go through 3D shape within the pharmaceutical research, the Applied Synthesis Technologies group at Pfizer, and introduce alpha methylated aryl acetic acid. I'll go through a couple of case studies, how we enable the process, and then how we scaled them up as well. So really, clinically successful compounds have an increase in 3D shape. This is something that our colleagues at Pfizer concluded when they analyzed the fraction of sp3 character in compounds at the various stages of drug discovery. Many of you have probably come across this paper, Escape from Flatland by Frank Lovering, and really it highlights the importance of synthetic chemistry in drug discovery and how those 3D shape does increase the synthetic complexity and the challenges of chirality along with it. And what we know for sure is that those well-precedented chiral motifs can prove challenging to access on scale. At Pfizer, one of the strategies that we adopt is utilizing our Applied Synthesis Technologies group. And really their remit is to work closely with medchem to support their delivery by installing those technologies early in the process so that they're available when needed for scale up later on. And they accelerate our delivery as a result. And they have a range of technologies available to them from parallel medicinal chemistry, reaction optimization, photoredox, flow, and biotransformations. And they can deliver from sub-milligram quantities all the way through up to kilogram quantities of API. Really developing those scalable processes and enabling those key steps. So chiral alpha-methylated AR acetic acids or AR propionic acids are common pharma fragments found in drug discovery, and they feature prominently in the profen drug class, as shown here. And there is a whole host of methodologies out there to access these motifs, and they keep appearing in the literature. Plenty of alpha arylation chemistries, and the methodologies that's employed really in this space can involve a range of chemistries from Friedel-Crafts all the way through to resolution to access compounds on tons of scale and manufactured per year. The activity lies in the S form shown here. For us, on our program, we were interested in accessing this 3,5-dimethoxy aryl acetic acid with the R chirality. And really the team brainstormed a range of chemistries that we can get there. And we prioritized chemistries that really could be accessible to us for large scale. So we wanted to prepare these compounds on 100-gram quantities, but also with the view of going further to kilogram quantities. And for that, we looked at resolution and these other asymmetric routes towards compounds. So just to start through the sequences that we explored, the resolution really gave us mixed results. The salt resolution shown here wasn't something that was readily scalable. After screening 400 combinations of chiral salts, what we saw was really, at best, this one hit of up to 95% EE from multiple recrystallizations. The hydrolase gave us more promising results. Here we were able to identify an enzyme to catalyze this process on 5-gram scale with good substrate loading. We got good resolution yields to a single enantiomer shown here with the ethyl ester. As a result, a second hydrolysis step would be required. Chemically, this led to erosion of EE. And so really, the enzymatic process was much more efficient, 99% EE and good conversions. So when we step back, what we see is that the starting materials in these cases would need to be prepared. And so that gave disadvantages to the resolution approach. And the end game here had a high step count. We did explore the auxiliary approach as shown here, and we were interested in this because of the low step count. It had high yields across the board. However, the starting material is quite advanced and so really quite scarce. We were able to push 100 grams through this sequence, but obviously with the limitations as shown in red, chromatography at each step, gums and oils as intermediates, cryogenic temperatures, it wasn't something that we could take on beyond those scales. As a result, we were interested in this asymmetric reduction approach, again, due to the low step count. And how we achieved this was starting from the AR bromide, which is readily available and very, very cheap and accessible on kilogram quantities. The initial methylation with electrophile quench was something that we studied. And we found that turbo-Grignard gave us poor methylation here, this electron-rich AR bromide. And butyl lithium, although gave us complete methylation, suffered from the basic organolithium that's generated and didn't react with our electrophile. It wasn't until we came across this magnesium lithium species that we were actually able to afford the desired reaction and isolate the tertiary alcohol shown here. The elimination was very well studied. We studied it in batch originally, and what we found was that high temperatures were required in sulfuric acid, and the reaction was very fast. When we analyzed the DSC data for the starting material and the product, it really showed at 153 degrees we were seeing an exothermic event. And really at Pfizer we want to be have that sort of 100 degree window, and so it limited the batch process. Flow is a terrific methodology that's available to overcome those safety concerns, and it also generate almost quantitative yield almost of the desired material. Because we're heating quite high, what we saw was very, very minimal side products associated with dimerization there, and generating our material quite nicely as a solid. The reduction, we studied that, and that was problematic in that chemically. We ran a series of screens on this hydrogenation with ruthenium and rhodium catalysis, and at best we could find conditions to generate 83% EE. And the enzyme here, overcoming those limitations, generated single enantiomer in good yields, which was really demonstrated on that 500 mg scale. The issue here is this whole cell. It really does limit scalability of the process, and so we needed to continue our exploration towards those scalable routes. One area we were really attracted to was the aryl malonate decarboxylase enzyme. And this is the wild-type enzyme isolated from Bordetella septica, and it has the substrate of this malonic acid. It generates a single enantiomer of the desired acid, theoretically 100% yield, and the wild-type is R enantiomer selective, and it operates between pHs of 8 and 9. The mechanism that this enzyme works has been heavily studied by professors across the board, including Kurist and Mickelsfield. And the proposed mechanism is that the substrate orientates itself in the active site where the large group, being aryl or alkenyl, resides in this sort of large pocket. The carboxylate, this one is stabilized by H bonding, and this residue residing in the small hydrophobic pocket decarboxylates to generate this ene diolate. The ene diolate is stabilized by H bonding as well as pi conjugation to the large group. And so really a cofactor isn't required for this process, and it's then protonated by the 15118 residue to give us the R acid. One issue with this process is the spontaneous decarboxylation of malonic acids, which generates racemic monoacid, and this erodes the EE of your reaction. So minimizing this process is really important for this reaction. We went on to demonstrate this on the bromo dimethoxy aryl, arylation of dibenzyl malonate, methylation to give us our dibenzyl intermediate, and then hydrogenolysis to give us the diacid, which we found was stable as a solid, and we could store that quite happily. This approach to access the diacid is something that was really coined by Kurist and others to avoid the saponification of the malonic esters to generate the acid, which leads to decarboxylation. With the diacid in hand, we can take this on with our AMDA in buffer to generate a single enantiomer of our monoacid in quantitative yields. And we're using lyophilized cell-free extract here, so this process is definitely something that we could go on to scale further beyond these 5-gram scales. And as in early discovery work, we find targets change, and it really does test how robust our chemistries are. We had this electron-rich derivative to prepare, and now we're looking to really access this heterocyclic variant. And what we know, and what a lot of you have experienced, is heterocycles bring a lot of challenges to our chemistries. They can coordinate in cross-coupling reactions. They're polar, electron deficient, and really it's an issue across a lot of chemistries, but certainly an area that we would want to have access to within MedChem. So we went on to scope the methodology that we had to hand, starting with the Evans auxiliary. We found really low yields of the heterocyclic derivative we could generate, and also the dicyl isomers here are inseparable. We can attempt the reduction, but the alkene is actually very unstable. It's challenging to access. The salt resolution generated D-threoninol as a hit. Unfortunately, it's not something that we can access on large scales. And the hydrolase resolution gave us, again, the R ester as a single enantiomer. Now we're getting really lower yields being projected there. Of course, the aryl malonate decarboxylase is something that we were interested in for this process. So we started with the aryl halide, generated the dibenzyl malonate after methylation to give us our intermediate in as a solid. Hydrogenolysis of the dibenzyl malonate gave us the diacid, which was contaminated with monoacid. Attempted isolation gave us complete decarboxylation to the racemic monoacid. Really, we asked two key questions. Could we stabilize this diacid for the subsequent AMDA step? And then whether this orthofluoro heteroaryl derivative is a substrate for AMDAs. We were very encouraged with our first results in this work. 100 milligrams of the dibenzyl malonate could be hydrogenated in aqueous buffer to the diacid as a solution. It was contaminated with monoacid at this step, but we could filter away the catalyst and add our AMDAs to that, and we're pleased to see 89% EE. Now, we were aware that the lowering of EE and the spontaneous decarboxylation was an issue, and so went on to study the stability of this malonic acid and potentially find a window of activity. We generated the malonic acid in aqueous buffer and adjusted that solution between pH 5 and pH 11, and we incubated the samples at 20, 40, and 60 degrees. The data I'm showing here is for monitoring the decarboxylation after 7 days, and what you can see is definitely a stable window above pH 8, below 40 degrees. And we noticed an overlap with the enzyme optimal activity there. And we're able to exploit this to generate a process. We could take the dibenzyl malonate, solubilize in toluene, add buffer, so we have that biphasic mixture, and we add 2 equivalents of sodium hydroxide to neutralize the diacid that's generated, and to make sure that the pH does not fall below 8. We can hydrogenate 20 degrees over 4 hours, and we have the diacid now in solution with the buffer. We can filter off the catalyst, separate the toluene, and introduce our enzyme. And what we were able to show on a 50-gram scale is this process is definitely viable. We get a single enantiomer, 80% yield over the 2 steps, and we could lower the enzyme loading there after a study. Something we were interested in was really beyond this 50-gram scale. Could we lower the catalyst loading further and reduce the volumes to improve the throughput for the process? And we were able to show on a 63-gram scale, we can go down to 5% with no detrimental effects on the EE. 120 grams, we can go on that 5%. We can adjust the buffer pH, and there's a nice window that we can operate in, and then take that further to 2% and lower volumes for really an improved process. We could really generate over 100 grams of the fluoro acid in single enantiomer high yields, really demonstrating that we can go far beyond these scales if needed. We were interested in scoping out the methodology for other heterocyclic derivatives, and we were able to show on a 200 milligram scale that we don't need to isolate the diacid even when it's stable. This process works well, and these other heterocycles are tolerated in the sequence, perhaps showing that more study on these other derivatives could generate a process for them as well. So really, to conclude, the efforts here, the MedChem team, process team, AST team, were really able to scope out those routes. I think it was something like 5 weeks, and then scale up to deliver hundreds of grams in about 3 weeks' time, really facilitating the project's delivery, and then the methodology being explored there for publication. Again, I'd like to thank all the members that were involved in this work. Certainly a team effort to deliver, and I'd like to thank you for listening.
Great.
Happy
Awesome.
to answer any questions.
Awesome. Thank you for that story, Caroline. I think we had. You want to run the Q&A? I have a question if I can put myself in the.
Yeah, well, I pull them up. Yep.
Yeah, Caroline. So great talk. I think like people think this is easy, and it never ceases to amaze me how every molecule has its own little story to tell. Do you know what I mean? Like whether it's resolution or whether it's, you know, application into other methodologies, there's always like a curveball with this. And so I just think it's like, it's just always remarkable to me. Like it makes me optimistic about job opportunities for organic chemists in the future, if you will. So, but my question to you is around, so it's nice, like you basically figured the sweet spot to do a through process, right? To hydrogenate and then apply the enzyme to decarboxylate. Is the end, are those two operations, those two chemistries incompatible with each other? So like, is there a scenario where you could actually like, you know, where you could see like coupling enzyme with, you know, the hydrogenation step, or is the hydrogenation step too stepwise? Like you just get a bunch of monoester or something to that effect? One pot is what
Carl,
I mean.
we did think about that, and you know, this enzyme is very robust. We added the enzyme to our buffered hydrogenation mixture. Our initial results here when we were trying to scope out, and we did see 46% EE at the end with the enzyme in the buffer mixture during the hydrogenation. So there could be a process there, but what we found was it's definitely cleaner to have the sort of the telescoped process where we remove the palladium and we have the buffered mixture and then introduce the enzyme. It was much more workable to do it that way for the scale up rather than have the enzyme present in the hydrogenation. Was that your question?
Yeah. I mean, it's just an interesting problem, right? The question goes through my head is like, is that a chemoselectivity problem or an enantiomer? It's probably a chemoselect. Like, there's just too much going on in the pot. Like, so if you almost want to go back to your flow solution, right, where you could separate these operations in space, right? Hydrogenate and then just run right into your amidase with a pH correction. It's cool. Yeah. Thanks.
Caroline, we've got quite a number of questions already for you. So the first one that came in is from Lady, who says, asks the first step of the asymmetric reduction approach. Did you try the turbo Grignard reagent instead of the butyllithium? When you're first making your malanates at the beginning, did you try the turbo Grignard there to make your malanates when you were adding to the adding the oxalates in? You have it there.
In this step,
yeah.
Yes, we did. We tried that, and we actually saw no methylation with turbo Grignard. Okay. We think that it's just too electron rich for that to go ahead and be productive. Butyl lithium was great. We could lithiate it, but obviously then it was just too basic. And it wasn't until we had the combination of both that we actually saw quantitative methylation followed by productive reaction with electrophiles.
Okay, thank you. And Kirk Shimkin is asking, how well are substrates other than alpha methyl tolerated? Did you look into anything beyond methyl?
So we did not look at anything beyond methyl. The enzyme itself works well for these other small groups, so methyl, fluoro, hydroxyl, and amino. But when you go into ethyls or bigger alkyl groups, I believe it's out of the scope for this enzyme unless there's bioengineered variants that could perhaps tolerate those larger alkyl groups. But no, for our project, we were interested in the methyl.
Okay. All right, what time is it? All right, so I'm going to skip a couple, if you don't mind. There is one question that I actually want to pose as a Twitter question. But how long did it take you to identify the AMDAs? Did you screen a lot of enzymes first?
Oh, okay. So the AMDAs is a single enzyme that's actually being isolated for this process. There isn't a panel of AMDases to screen.
Okay.
There are bioengineered variants of the wild type that can access the S chirality, amongst others, to racemize and so on. But there is just one of the enzyme available.
Okay, and let's see. From Greg Hughes, his question of, did you evaluate E reductases for your electron deficient substrates? Or was that after you had already identified the AMDs?
Sorry, Scott, what was the question?
Did you evaluate E reductases for the electron deficient substrates?
Oh, okay. So we actually didn't have an opportunity to evaluate the E reductase because, if that was the question, because really getting access to the acrylic acid is very challenging. So that chiral reduction was not something we could explore deeply.
Okay. And there is an interesting question. Thank you, Caroline. It's awesome. That's great answers to all these questions. I do want to say there is somebody who mentioned a question here, which is a general thought about, it says, when students are thinking about the future of biocatalysis and organometallic catalysis, should they focus on one area or try and have experience in both? And I think that's a super interesting Chem Twitter question that I think we'll put out there later on for people to join in later on. But Caroline, thank you so much. That was a wonderful talk, and really appreciate you coming on here and joining us today.
Thank you so much for having me, Scott. I'm looking forward to hearing Mary's talk.
Yeah, here we go. So Carl, after you.
I'll take it away. I don't know. Why would you limit yourself? Maybe you need to study one aspect of this, right? But like, I always feel like people like limit themselves. Like, I'd be curious. I'd want to get, this is the 50-year-old me talking, not the 20-year-old me talking, but like, I'd want to get experience with all this stuff. So, but yeah, great talk, Caroline. Thank you so much for sharing it. And, you know, like, I think like folks you can't underestimate the need for speed, which I'm sure you go through every day, right? Like, to get that 100 grams, you know, the first 100 mgs is that some people say the hardest, but the next 100 grams can be pretty challenging when you have your colleagues looking for material. So I get the pleasure of introducing Mary, Professor Mary Watson from the University of Delaware, who, you know, I think in way of like the standard introduction, Mary, I was going through your bio, and like, I kind of knew this, but like, you've got like a great, like, it's, from my perspective, like, it's just an awesome pedigree. You've had like a lot of really cool from undergrad experiences working with Professor Dave Evans, getting your PhD with Professor Overman, and working, doing your postdoc with Eric, and just, you know, just an awesome background. The thing that came to my mind, Mary, is we've known each other for a long time, but I can't actually remember when we met. And I feel like I went to grad school with you, but I didn't. Like, that's very clear. So, and you know, so
you were a TA when I was an undergraduate.
Oh, I'm sorry.
You were head TA, I think.
Oh my God. I'm really sorry. I'm sorry. I'm sorry.
No, I'm sorry.
Still in chemistry. That's a good thing. That's a good thing, and not harmed in lab.
That's right.
Well, so okay, so that goes back a long time. But I think the other thing, Mary, the connection, we have the Jacobson connection, the Harvard connection, but also, like, you're a professor at University of Delaware. I'm a blue hen, very proud blue hen. And I don't know whether it was this talk was in May, but like, I was reflecting, I think we were talking about this before. I had the honor of giving like a chemistry commencement speech at Delaware. And and so I was like, I've been thinking a lot about Delaware in general, like over the spring. I don't know why. Maybe it was this talk, maybe it's other things. But we were talking about this whole, like, I think that the theme of it was like, how do you know you're a chemist? Do you know what I mean? And like, you strike me as you knew you were a chemist, like almost in high school. Do you know what I mean? Like, but I thought I would pose the question to you, like when at point, like what point did you actually say, like, to your, like, we were talking before, like, you said to your parents, like, I'm a chemist?
So I had an amazing high school AP chemistry teacher Miss Lisa Blowers. And I think that's when I thought I wanted to be a chemist for the first time. Because, and this is maybe a little masochistic, she made us work really hard. And there was never a dull moment in that class. And she let us do, but she let us do amazing things with that hard work, right? And so I think that was my first time really getting pushed to think as hard as I could about something and also get to use my hands to make stuff happen.
Yeah.
I was hooked. I thought that was just a fabulous combination.
It's remarkable how these people, like for me, I certainly had high school teachers. I definitely had Professor Burmeister, JB, who your colleague, he was totally influential for me. Well, the whole Delaware experience was. I mean, it was just a great place to go and become. When did you say now I am a chemist? Like now, was it after senior year in high school?
No, I went through a lot of self-doubt in college. Probably like many people. I was going to go into social work and social justice. So I was an AmeriCorps Vista person for a year after college.
Okay.
And then I think probably my first year of grad school, I was standing next to Chris Douglas, a professor at University of Minnesota now, at his fume hood. And I remember just talking to him. He was a couple years ahead of me in grad school, and feeling like that was exactly the place I was supposed to be. And I don't know, anybody who knows Chris probably has had that experience, that he just makes you feel like you're where you're supposed to be. But being in the lab, getting to work with other people who are really passionate about what they were doing, I think that's probably when I knew
it all clicked, and you're like, hey, this is me. I'm a chemist. Yeah, it's pretty amazing. Like chemistry people have a thing, like we all have very poor social skills, right? That's a stereotype. But in fact, it's people like just any other endeavor in life that drive this. So it's nice. Thank you for sharing that. So I think with that, I'm glad you're a chemist, and I'm also really glad you're a professor at the University of Delaware. So I think I'm going to turn it over to you to give your talk, and you can take it away, share your slides, and we'll see you on the other side.
Thanks, Carl. I think that was the most fun introduction I've ever experienced. So definitely raising the bar on how to get people introduced. So thank you very, very much. And thank you to the Division of Organic Chemistry for the opportunity to be here. And thank you very much to CCHF for sharing your resources with us so that we can meet this way. I think it's really special to be able to meet with people all over the world and share my chemistry with you. And so the story I'm going to tell you about today is done by an amazing group of people. And so I'm really excited to tell you about our efforts to make deaminative cross-coupling reactions a thing. And this is a story that's been ongoing in my group for a while. And it really started with our inspiration from palladium catalyzed cross-couplings. And so 2010, when Professors Heck, Negishi, and Suzuki won the Nobel Prize, was my second year at University of Delaware. And it was the first time I went at 10 in the morning to buy a case of champagne in this job. But if you're thinking about being a professor, it's not the last time. So great job, good benefits. And so there's two things that really are exciting to my group about these palladium catalyzed cross couplings. The first is, of course, the tremendous amount of mechanistic underpinnings that we have for how a palladium catalyst can activate an sp2 carbon to halide bond and convert that into a carbon-carbon bond. And the other thing that's really inspiring to my group is how perfectly this methodology overlays a synthetic need. And so, of course, traditionally with pharmaceuticals having a lot of unsaturated carbon atoms, this has been a well-used set of methods for making those molecules. But as Caroline just really beautifully introduced in her introduction, pharmaceuticals have increasing content of saturated carbon atoms. And so this presents a really exciting opportunity for chemists now to develop new methods to be able to do cross-coupling similarly to what's been developed with sp2 hybridized carbons, but now with sp3 hybridized carbon electrophiles. And when we started in this area, and I'll talk a little bit about this, what we really thought was exciting here was, of course, that if you have a saturated carbon atom, these could be stereo centers in your starting material, and you may be able to do stereo-specific cross-couplings to deliver highly enantiomer-enriched products. And the story I'll tell you is that my group has really pushed me and forced me to evolve in terms of thinking about what types of chemistry are most impactful. And so one of the exciting things for me is that we've started thinking beyond stereochemistry, if you will. Hopefully that isn't offensive to anybody, but also thinking about what are the starting materials, what are the X groups here that would be useful to have and haven't yet been developed. And so we've been thinking about essentially new feedstock classes for cross-coupling chemistry. And in particular for this talk, I'm going to be focused entirely on breaking carbon-nitrogen bonds to deliver carbon-carbon bonds. So when we started this, as I said before, we really thought about stereochemistry as the main reason you might want to use an alkylamine as your feedstock class. And in particular, we thought about the fact that benzylic amine is readily available in exceptional levels in enantiomeric purity. And so if I'm being honest, we buy many of our enantioenriched benzylic amines, but if we have to make them, we actually use a chiral auxiliary approach. We use we use this auxiliary, and we can deliver these types of products essentially in perfect enantiopurity. This chemistry, I'll point out, is amazingly robust. Because of course you're isolating a diastereomer at this stage, all you need to do is purify your diastereomers. You don't even, and then clip your auxiliary. You don't even need chiral HPLC to know that you have an enantiopure amine at this point. And so this is chemistry that's just really beautiful in how convenient and robust it is, and that you could run this essentially in any chemistry lab in the world. And so we wanted to take advantage of that fact. We wanted to be able to take these highly enantioenriched benzylic amines and clip the benzylic carbon-nitrogen bond to have this benzylic piece enter a cross-coupling reaction. However, everything we tried to do to break this benzylic carbon-nitrogen bond failed. And so the first postdoc in my lab, Dr. Prantik Maiti, and the first person to get her PhD from my group, Danielle Shack-Lady-McAtee, collaborated to design a way around this problem. And they actually took advantage of something we try to convince sophomore organic students happens, but here we did it on purpose. And so we simply over-alkylated our tertiary amine to make these trimethylammonium salts. And we envision then that these sorts of trimethylammonium salts to be able to enter a similar catalytic cycle as the one that has been beautifully developed by Professor Liz Darbo's lab at UC Irvine, where an electron-rich achiral nickel catalyst does an oxidative addition step, in this case with inversion of stereochemistry, delivering some sort of benzylic nickel intermediate, which could then undergo the transmetallation and reductive elimination to give our desired product. So this was exciting to us because it would allow us to use these highly enantioenriched benzylic amine precursors. It was also exciting to us because we thought that we'd be able to get away with using an aryl-boronic acid as a coupling partner. And it turns out that at the time we were working on this, that was something that really hadn't been done to make highly enantioenriched benzylic products. And the reason we thought we could get away with this weaker transmetalliting agent, if you will, is because we thought that we could tune the electrophilicity of this nickel center. And so if you imagine the transmetallation occurring through two steps, where the borate first coordinates to the nickel and then you do an intramolecular transmetallation, you could accelerate the borate coordination to the nickel if the nickel's under-coordinated, if you will. And we could tune that by this counteranion, which would ultimately come from the ammonium triflate. And so if we made this nickel electropositive enough, the borate coordination should be fast, and we should be able to get away with using the boronic acid. And this does seem to occur quite nicely. And so everything about this reaction working all comes down to design of reagent. When we first started in the group, I thought I designed new reactions. Now I'm pretty convinced we design new reagents and demonstrate that they work in the reactions you want them to work in. And so under these sorts of conditions, we can take these benzylic ammonium salts, which are essentially enantiopure, so greater than 99% EE. And we can do these sorts of cross couplings to deliver a range of products. And you'll note some of the functional groups, including the ester, nitrile, and sulfone, are things that would be hard to install if you were using a Grignard coupling partner instead of the aryl-boronic acid. This chemistry is also effective for vinylations, and this is one of my favorite examples because in this stereospecific chemistry, we actually get better stereochemistry, better EE in our products if we have lower catalyst loading, which is the opposite of every experience I had ever previously had with asymmetric catalysis. And so here you can see that most readily with 5 mol% nickel, we see only 77% EE in this vinylated product. But if we drop the catalyst loading 5-fold, we get essentially nearly perfect stereochemical fidelity. And this is consistent with a nickel-mediated epimerization pathway, wherein one nickel may displace the other nickel from a benzylic nickel intermediate. However, there are some limitations to this chemistry, and there are things that we are continuing to focus on. The biggest one is that this naphthyl group is really important to getting high yields in this chemistry. And so if you don't have it, if instead you have this parafluorophenyl group, although you'll still get good stereochemical fidelity, so 95% EE in this product, the yields are poor. And so this is actually typically observed across the board in stereospecific cross-couplings of benzylic electrophiles. The vast majority of the substrates that give high yield either have these sorts of extended pi substituents on them, or they have 2 aromatic substituents here. You can see we've played with this a little bit. So a second generation of the catalyst system does increase our yield, but our stereochemical fidelity does go down. And so this isn't ultimately a perfect solution. Nonetheless, this does tell us something mechanistic, and this is actually a proposal that is very, very similar to what Professor Liz Jargo has proposed with her alcohol-derived substrates. The reason the naphthyl is likely required is because that naphthyl group interacts with the nickel catalyst, probably first via pi coordination, and then the nickel actually likely breaks the aromaticity in what we call an SN2 prime type oxidative addition. And so, of course, partially breaking aromaticity of the naphthyl ring costs much less energy than fully breaking aromaticity of the benzene ring. So at this point, we are pretty excited about this chemistry. We had been able to deliver these highly enantiomer-enriched diarylated alkanes, and we'd also developed a borylation reaction. But we had some frustrations. So the first was that it turns out, I hate naphthyl groups. I really wish all of our products did not require those to be in there. And I'll just hint that we have a paper coming out with a solution to that problem pretty soon. But we also started to get frustrated with needing these to be benzylic at all. And we started to ask the question, could we do similar reactions where you didn't benefit from benzylic activation of this carbon-nitrogen bond? And we were really excited about this. So as we started to look through the literature, of course, there were some beautiful examples where people activated sp2 carbon to nitrogen bonds, including breaking the strong amide carbon-nitrogen bond. In terms of sp3 carbon to nitrogen bonds, there were electronically activated examples, including our own work. And there was also examples independently by Abby Doyle and Tim Jamison's groups, where they showed that you could harness the strain in these carbon-nitrogen bonds of aziridines to break those bonds. But in terms of alkyl groups that didn't contribute to the activation of the carbon-nitrogen bond, there really weren't any examples. Now, in all these examples, please note the nitrogens are all activated. So unactivated here is a misnomer. It's just the fastest way to say that the alkyl group is not pushing the carbon-nitrogen bond cleavage. Now, you might argue that the reason that nobody's gone after these unactivated alkylamines as cross-coupling substrates is because you don't need to. If you want to do a cross-coupling to install an unactivated alkyl group, dating back to the early 2000s with Greg Fu's work, there have been great ways to be able to install these groups. And you know, I kind of feel like every time I open JAX, there's a new way, right? There's a new activating group, and they're beautiful. And so we thought long and hard about whether or not somebody really would want to take the alkylamine. And I have to give full credit to Corey Bosch, who graduated from my group several years ago and started this project in my lab. My role on this project was to remind him of everything the Fu lab had ever done with alkyl halides and ask him why his stuff was better. And Corey got really tired of me asking this, and so he made me a slide so he could remind me when you would want to use alkylamines. And when we started this project, we were having lots of internal conversations within the group about why you would want to use an alkylamine. And so, of course, Corey reminded me there's great ways to make them. But we also were cognizant of these complex products or fairly complex drug-like products like Tamiflu. And Carl was talking about Januvia earlier. This is one of my favorite examples of an alkylamine. And we were also aware, of course, of biomolecules like dopamine or lysine that have amines in them. And what we came down to is you would use the amine when you had the amine. And so maybe that's particularly good for late stage functionalization. We can all agree that an alkylamine, particularly if it's suitably protected, could be carried through a multi-step synthesis in a way that an alkyl halide might present more challenges for. And so something that's been really exciting on this project is that as we've developed this chemistry and started to talk outside the group about it, people have told us that we have a lot to learn. And in particular, people in the pharmaceutical industry have helped us with this. And so Michelle Garnsey from Pfizer got a shout out in the last talk. And I also want to give her a shout out because she actually, after one of the very first times I talked about Corey's work, told me, Mary, stop giving Corey a hard time. We have a lot of alkylamines in our monomer store, and we would love to be able to use these for a wider variety of reactions. And so it's been really exciting for us to realize that these precursors are not just good for late stage functionalization, but also quite effective as simple building blocks. Okay, so we thought we had a good reason to do it. How are we going to get it done? And we had some real problems here. So one of the big problems we have is that we can't use an ammonium salt. There's multiple reasons for this, but if you're just thinking about the catalysis step, the oxidative addition step, that's going to be one of the major hurdles. So first off, I told you before, our nickel catalysts add in an SN2 prime type fashion. And so we've never found a nickel catalyst that's nucleophilic enough to directly break the carbon-nitrogen bond. So that would be one hurdle we'd have to overcome. If we did overcome that hurdle, it's quite unlikely that the nickel catalyst is going to attack the bosterically hindered carbon. Much more likely it would attack one of the methyl groups. And even if we're quite clever and come up with a really small nickel catalyst that doesn't care, we're still only getting 25% selectivity for the carbon-nitrogen bond we want to break. And so like any good advisor, I came up with a solution. We need a new way to activate the amino group. And like any exceptional graduate student, Corey actually found the solution. And so Corey went and dug into the literature and he found this report from Ellen Katritsky's group, wherein they convert primary amines quite easily into 2,4,6-triphenylpyridinium salts. And these are then suitable electrophiles for kind of classic SN2 type reactions. And so if you squint and imagine Ni instead of Nu here, this was the type of SN2 type reaction that we wanted our nickel catalyst to do. I'll just comment briefly on how we make these. So you can buy this 2,4,6 triphenyl salt. It's a little bit expensive, and it turns out that if you've just published your first paper on it, it's going to be back ordered for 3 months. So, which is going to freak you out in terms of other folks competing with you. So you can, you can make it yourself. It's a condensation of 2 equivalents of acetophenone here and 1 equivalent of benzaldehyde. That reaction actually does work fairly well. And then you can take that beryllium and condense it with your amine. We often use a slight excess of the amine so that we are not worried about separating the 2 salts. But if your amine is precious to you, you can run this with 1-to-1 stoichiometry, and you can do normal phase silica gel chromatography to purify your pyridiniums. The most important part, though, of this activation mode of the amine is that it's chemoselective for primary amino groups. We can have tertiary amines, we can have protected nitrogens and other Lewis basic groups in our molecule. And of course, what this means then is that we're starting to be able to incorporate functional groups that are important for pharmaceutical development. And I'll just note that was not true for our ammonium salts. We were adding methyl triflate to alkylate those, which obviously would have some chemoselectivity problems in this type of molecule. So with these types of substrates at hand, Corey started optimizing this reaction, and he started with conditions that were quite similar to what we'd seen work well in our stereospecific cross couplings, and we saw that they essentially failed. And as he continued to look at this, what we realized is that the conditions that we came out at with the nickel-2 precursor and these types of bathyrophenanthrene ligands were much more similar to what Greg Fu had used when he was doing activations of alkyl halides. Consistent with a pretty dramatic change in mechanism from a stereospecific 2-electron oxidative addition to a stereoablative 1-electron, single electron transfer step to break this carbon-nitrogen bond. And I'll show you that mechanism in a minute. Under these conditions, we were able to tolerate a pretty amazing, for me at the time, pretty amazing substrate scope. So we could tolerate both primary and secondary alkyl groups on the alkyl pyridinium, including acyclic examples, secondary examples which are more prone to isomerization events. You can see some of the examples of functional groups like the aryl chloride. We were quite determined to put in heteroatoms and heteroaryl groups, as you can see here. And this included not only the indole, but also 3 and 4 pyridyl groups. But if I'm being really honest, most of the examples on this slide you could probably do from an alkyl halide. And so I just wanted to show you one example, it's my very favorite one, of when you have the amine, and so you would use the amine. And so of course, this is Lipitor. You know, you don't have to dig in the patent literature to know this is a real medicine. And this is the amine intermediate used in its synthesis. And so we bought this amine, we can make the pyridinium salt, and we can do the cross coupling. Now, the yields here are somewhat low. Fortunately for us, the 3 phenyl groups here are going to prevent any process chemists from wanting to use it anyway. And these low yields are not so problematic for a medchem application. And so, so the chemistry, I guess, is useful, but that's, you know, of course, the low yields are not why this is my favorite example. The reason it's my favorite example is that if you compare the structure of Lipitor and Crestor, of course, there's this double bond difference, but of course, Crestor has this electron deficient 6-membered heteroaryl group, whereas Lipitor has this electron-rich pyrrole. And so if our chemistry had existed when Lipitor and Crestor were being developed, you could have used a common intermediate to make the pyrroles, but also to break the carbon-nitrogen bond to install electron-deficient 6-membered heteroaryls to make dihydrocrestor derivatives, if you will. And so that's just a little bit of a retrospective analysis of when you might want to use this sort of chemistry. In terms of mechanism, we have evidence for an alkyl radical intermediate, and we're still looking into what the nickel species are that turn the cycle over. But one possibility is the so-called transmetallation first mechanism, wherein a nickel-1 species undergoes transmetallation and is then poised to donate an electron into the pyridinium ring. And so, of course, the pyridinium is not just a good leaving group, it's also an excellent antenna to accept that electron. That would generate this dihydro radical, which can fragment, releasing triphenylpyridine and the alkyl radical. This alkyl radical could then recombine with the nickel-2 intermediate, and reductive elimination then completes the catalytic cycle. We have evidence for this alkyl radical intermediate from isomerization of enantioenriched secondary alkyl pyridiniums, as well as a tempo trapping experiment and radical clock experiments. And as I said before, we're still nailing down the rest of these pieces. But the thing that this cartoon mechanism gets us, of course, is the ability to think about what are the other inputs that we can put in, what are similar catalytic cycles wherein we could harness this single electron transfer type mechanism and have this alkyl radical do productive chemistry. And so that's what I'm going to focus on for, I'm going to tell you just a few vignettes. And all of them center around the idea that we want you to be able to take an alkylamine and convert it into anything you want. That amino group, you should think of it like it could be anything now. And that's our goal. And we're really excited that we've made some progress on that. So one of the first progresses we made on this was actually expanding what you can do in terms of making sp3 to sp2 bonds. And this was one of our collaborative projects with Michelle Garnsey, Joe Tucker, and Brian Bosco at Pfizer. And so we were, as I showed you before, we could do a Suzuki-Miura type cross-coupling with aryl boronic acids. And what Michelle asked us was, could we switch this and use an aryl bromide instead? And their motivation was that they have about 10 times more aryl bromides than boronic acids and esters. And so they were excited then to be able to harness the diversity present in these coupling partners, and that would be exciting for their medchem efforts. Now, from my perspective as an academic, I have to be honest, we used 20 boronic acids in our original paper. We're never going to use even 6,000. And so this was not our main motivation. Our main motivation was the fact that there were certain functional groups that we could not tolerate under our basic Suzuki mirror cross-coupling conditions. So in particular, any pyridinium salt that has an electron withdrawing group at the beta position simply underwent elimination in those cases, giving you essentially a really expensive way to install an alkene. We also couldn't tolerate, acidic stereocenters. These epimerized under those basic conditions. And so, of course, we started to think about reductive conditions, particularly those similar to those developed by Dan Weix's group, which would occur under neutral conditions and potentially allow us to overcome some of these problems. And so Jenny Lau led this project, and what she found was that with primary alkyl pyridinium salts, indeed, we could do an arylation under these reductive conditions using manganese as a terminal reductant. But when she switched to secondary alkyl pyridinium salt, she saw much lower yields of the desired product, and instead started to see these byproducts, which we now endearingly call the 4-addition byproduct, because it likely arises via that alkyl radical, so the isopropyl radical, adding to another equivalent of pyridinium, and then being reduced by one more electron to give these sorts of byproducts. Trying to understand where these came from, Jenny ran a series of control reactions, and what she found was that if she left the nickel catalyst out, she still saw this product in about the same amount. Of course, she didn't see any of the desired cross-coupling product, which is requiring the nickel catalyst to turn that part over. And so what this came down to then is that it appears that manganese itself can do the electron transfer into this pyridinium, and that's generating these secondary alkyl radicals, which are more stable than the ones we would get from the primary alkyl groups, as explaining why we don't have a similar problem with primary alkyl pyridiniums. And so what this comes down to then is that we want that isopropyl radical not to find another equivalent of pyridinium. We want it to find our nickel-2 intermediate. And so to control then the relative concentration of the pyridinium versus the nickel-2 intermediate, Jenny did a slow addition of the alkyl pyridinium salt. When she initially did that, she started to see homocoupling of the aryl bromide. And so she fixed that by simply making one solution of both pyridinium salt and aryl bromide and adding these together to the rest of the reaction component. And that led to an 84% yield of desired product. And I just wanted to highlight a couple of examples of what we can now do because of that chemistry. And so I'll note this ester as well as this trifluoromethyl example. Both of these would have previously undergone elimination under the basic Suzuki mirror cross-coupling conditions. You can see as well that we can tolerate protic functional groups, which was another problem that we couldn't have done under the previous conditions. These are some of our more interesting examples. And so one of the really fun parts of this is to essentially look for all the interesting amines that you can get your hands on easily. Amlodipine is our current group record for functional groups that I said shouldn't work, and my students got to work. So that's an ongoing little challenge that we have in the group. So, certainly I didn't think this, Hunch type ester or the aryl chloride should be tolerated, and it works well in this chemistry. So under these conditions, okay, so what we've shown at this point is that you have at least two options if you want to make an alkyl aryl bond, and I'll point you to a few additional references. For some related reactions that came out at the same time. We were fortunate to be able to publish this work back to back with Ruben Martin, and Gary Molinder has a beautiful photoredox catalyzed process to solve this problem. In addition, Magnus Ruping and Professor Pan have a process that uses aryl iodides as a coupling partner. But one of the other exciting parts that came out of looking into these reductive couplings is a collaboration with the Weix lab. And so we have really convinced ourselves that the ability to use alkylamines is powerful, in large part because of the diversity and ubiquity available in this feedstock class. And of course, if you're looking for other feedstock classes that are equally diverse and available, carboxylic acids readily come to mind. And of course, this diversity is well appreciated. Amide formation is actually one of the most used processes in medicinal chemistry, as reported in this Nature review paper. And we would posit that that's due in part to the substrates that you harness for this and how available they are, as well as the reliability of the reaction. And so talking with Professor Dan Wykes, we started to ask the question, could we use the same feedstock classes, but instead of delivering amide linkages, deliver ketones? In other words, could we provide a method to access ketones with the same diversity of the substituents as you currently can get with amides? And as we thought about how to do this, we were going to use Dan's activated ester chemistry as shown here. And if you think about the other groups that you might add to an activated ester, like an alkyl zinc halide or a reductive reaction with an alkyl halide, none of these classes of substrates are as abundant as the alkylamine. And so we thought that there would be some space for the development of this reaction. And so working with Zhang Wang in Dan's lab, my student Megan Horner developed this reaction. And I love this slide because I skipped over all the simple substrates. These are the wildest molecules my group has ever contributed to making. Zhang and Megan went nuts. They essentially found, the most complicated pieces they could and started putting them together, making these sorts of Franken molecules, if you will. And so the way this chemistry works is that Zhang found that you could take the carboxylic acid and in situ convert it to the acyl fluoride. Of course, these are actually fairly stable. So if you want to isolate this, that's fine. But you can also just use it in situ and do the cross coupling to deliver these ketones. And this is, like I said, just a really great example of how you can take advantage of the diversity of the carboxylic acid and the alkylamine to make some really, really complex products. Okay, so both of those examples are sp3 to sp2 cross couplings. Of course, we're also very interested in alkyl-alkyl cross couplings. And as we thought about doing this, we really looked to the precedent with other electrophiles in developing Negishi type alkylations. And so Dr. Shane Plunkett in my lab worked on this. And he found some really great conditions. It uses tri-terbutyl terpy ligand to cross-couple primary alkyl pyridiniums with primary alkyl zinc reagents. And as you can see here, his functional group tolerance, again, was quite good. Actually, one of my favorite examples is the one that's least functionalized. It's this methylation, whereby we can take the amino group and convert it to a CH3 group. But when he took these conditions and applied it to secondary alkyl pyridinium salts, the chemistry no longer worked. And so looking in the literature, we found that 1-BBP was a ligand that's been used in sterically encumbered Negishi cross couplings before, both by the Fu lab and by the Visick group. And so we thought that that might also be appropriate in this case, and it turned out to be a great solution. And so the substrates scope I'll point out on this slide was this methylene B-pin example, wherein now you can, of course, use this carbon-boron bond for further elaboration of these products. Okay, so the last story I'll tell you is one that we're just getting ready to submit for publication. And this is one that was truly inspired by Reviewer 2. Okay, so this one goes out to Reviewer 2. And anybody who's ever submitted a paper knows that Reviewer 2 is the one, or submitted a proposal. Reviewers 2 seems to always be the one who tells you it's cute, but nobody's ever going to use it. Nobody wants it. And so in particular, when we started working on this, we got a lot of comments about who wants to take nitrogen out of molecules. Nitrogen's often the most important atom in terms of biological activity. And we appreciate that and agree with that. And so kind of sparked by that question, we started thinking about how about instead of taking the nitrogen out, we move the nitrogen around. And so in particular, you could imagine a 1-carbon homologation approach where you would start with an alkylamine. Hopefully this is something a little bit more complicated than just a long alkyl chain. And you might just want to add 1 carbon to it to see if this is a better molecule. So in the context of drug discovery, maybe you've gone through a great synthetic route, you have this alkylamine. If you want to see if moving that nitrogen a little bit matters, you typically would have to go back and resynthesize from the beginning with new starting materials. And so we thought maybe there's a way that we can just use this amine directly to do that 1-carbon homologation. Now, you might be skeptical, how much does one carbon matter? And so I really like this example of beta-alanine versus gamma-aminobutyric acid. And so the only difference between these two molecules, of course, is one methylene. And this has dramatic implications, not only in how much sigma Aldrich is going to charge you, but also in the biological activity. So essentially, there isn't biological activity in beta-alanine, whereas this aminobutyric acid is an anticonvulsant. And these are both really simple molecules, but it just really demonstrates how one carbon can make that difference. And so the way we wanted to do this was to have the key step be a cyanation reaction. So we would start with those amines, we'd make our Kuczewski pyridinium salt, do a cyanation, cross-coupling, and then by reduction of the nitrile, we would get to that homologated product. And of course, it's worth pointing out here that the homologated product is not the only interesting product in this pathway. The nitrile itself is quite important and found in a wide variety of valuable molecules, and of course can be converted to many things, not just this reduced amine. In terms of conditions, we are really inspired by this report from the Zhang and Liu labs, where they can take alkyl chlorides and do these cyanation reactions. And importantly, the zinc cyanide is a less toxic source of cyanide than some of the more traditional options. And so using similar conditions, Jianyu and Cameron were able to show what I think is really beautiful scope in this cyanation reaction. Again, everything on this slide is a more interesting, or you can name the starting material that we were using here, just demonstrating the scope. And we've also shown that you can indeed take this through a telescoped sequence. So we do need to do some filtrations and solvent switches here, due to incompatibility between the steps, but you can in fact run the pyridinium formation, do a quick filtration, solvent switch to DMSO, do the cyanation reaction, do a filtration, solvent switch, and do the reduction, trapping it as the Bach protected amine. And the yield here for the telescoped sequence is quite similar to the one in which you would carefully purify each of your intermediates. So with that, I'll just summarize. I hope I've convinced you that every once in a while, you might want to use your amine for something besides being an amine. And I also wanted to highlight the fact that we're not the only people, and nickel isn't the only thing being done with these alkyl pyridinium salts. So these are not just pseudo-halides. People have discovered that using photoredox as well as electron donor acceptor modes of activation, you can do amazing things with these types of intermediates. And we continue to be impressed and inspired by the work going on in a number of groups around the world. So with that, I will thank my group. I obviously didn't have time to talk about everybody's projects, but they are amazing, and they are the best part of every day of my job. I need to thank my collaborators. I've tried to highlight the ones whose works I've presented throughout the talk. These agencies for funding, and if permitted, I just want to tell you about my hobby, my COVID hobby. Some of you guys may have learned to bake bread. I'm learning how to organize virtual meetings. And so I just wanted to invite you to come to the Mid-Atlantic Regional Meeting, which is in early June, and to come to EWalk, which is in late June. And in particular, if you're a dude and you're wondering whether or not you're welcome to come to EWalk, you are. We very much want everybody in our community to feel welcome to participate in the discussions and how we can make organic chemistry a more inclusive place for everybody. Thanks very much. I'm happy to take any questions if we have time.
Yeah, wow, awesome. Great job, Mary. I love reviewer too. Like, can we talk about reviewer? Can we just talk about the whole mindset of like, why would you want to take an amine and turn it into something else? Right? Like, because it's fascinating to me. And I think it's kind of a problem with the field, right?
So, to be fair, I was reviewer too on this project, and Corey convinced me, and then Michelle convinced me. So I think one of the things that I've really learned through the pyridinium work is that academics don't know what people in pharma want. And I think it really highlights an opportunity where we can communicate in a different way and maybe share problems differently. because I totally, like, I expected that comment, right? Like that was my comment to Corey, right? This grad student who was trying, Corey's fearless and tenacious, and it didn't bother him. He just thought
you didn't squash Corey. Aren't you glad? Like, you didn't crush his moment.
You can't squash Corey. I mean, he's incredible. And, any grad student out there, you know what that's like when you come up with this great idea and your advisor's like, cute, but have you seen this paper? Right? Like, let's talk about it. But, I would say, I think it was really important when we talked about it, because our chemistry was better because we looked for those specific examples where we could really make the case, right?
Yeah.
This is when you want the amine. And so, I think reviewers too is really important. And I think being able
let's talk about the yes but, right? Like, versus the yes and. Like, I think that's the point. Like yeah, you need the reviewer too to push on you, but like, I think in general, like, I would not have like, I love the idea you got to the end of, like, let's take amines and carboxylic acids and make, like, this is something now you can do. And it started off from like what, like, many of us would say, okay, you're removing an amine to make, like, it seems counterintuitive. And I just think it's like great encouragement for people to be open-minded and curious at all points, and not talk about like what's better or what's worse. Like, even I think at one point you're like, this isn't ready for a process chemist. Like, process chemists are I can speak because I am one. We're the worst in this, like, in some ways. So I thought it was awesome.
Thanks very much.
We had a couple of questions. The first, one of the first ones was around from Kirk Shimkin, asking about, like, how difficult is it? You talked about how to make that activation, to make the triaryl pyridine starting material. How hard is it to get rid of all that stuff at the end of the reaction?
It's not. So the triphenyl pyridine byproduct is actually quite nonpolar. So for the first time in any chemistry, I've made beautiful chiral grease my whole chemistry career. And so for the first time ever with these pyridiniums, we're able to bring in essentially heteroatom content that gets us into, much greater polarity. And so, yeah, my students do not complain about the purification of the cross-coupled product. If they complain about anything, it's when the pyridinium doesn't just precipitate out, and they have to actually run a column on it. So, but often you just triturate the pyridinium salt, it precipitates out, and you use it, right? So, I guess my students are used to the idea you shouldn't have to run a column on that starting material. But yeah, we don't usually have problems purifying those products, the cross-coupled products.
Very nice. Yeah. No, I think like the stuff that don't apologize. Like, it's actually a nice handle too, right? Like, to put on your compound, isolate it, and all that stuff. And
it's
like
way greasier than you would think a salt should be.
Yeah.
It's really neat, I think. And there's actually a bunch of questions here about different types of pyridiniums that you're making, obviously. But I wanted to kick that off with when you make them, do you guys see elimination? Like 2 olefins, is that not an issue with these? But the main question you're seeing here, there's like 3 of them about, what do the electronics or the sterics of the pyridiniums, what role do they play?
Yeah, these are great questions. I'm really excited about them because we have a paper that's under review right now that's in collaboration with Marissa Kozlowski and Joel Rosenthal. And so where we're studying the effect of substitution on the pyridinium, specifically on the carbon-nitrogen bond cleavage step. And so I will, I guess, backing up a little bit, so if you read back in Kotritsky's work, Kotritsky actually proposes that the 2,6 diphenyl groups are important because they elongate the carbon-nitrogen bond. And Marissa Kozlowski has seen that in her own calculations. And we also see that they pre-orient the pyridinium towards the transition state for carbon-nitrogen bond cleavage, which is really cool, right? So essentially those groups help to force the carbon-nitrogen bond to cleave. The electronic effects are what you would expect for the single electron transfer step, but they're actually opposite for the carbon-nitrogen bond cleavage. So there's 2 steps to break that carbon-nitrogen bond. You've got to get the electron in there, and so electron withdrawing groups help for the single electron transfer step. But then you've got to break the carbon-nitrogen bond, and it turns out that electron-rich groups help that step. And so, those electronic effects then are generally not as important as the steric effect. But there's things we can't do with the 2,4,6 triphenylpyridinium. And so we are looking at other examples. And there are, because there's certain things we'd like to be able to do that we can't do yet in terms of substrate scope and things like that in the alkyl group.
Yeah.
But yeah, we hopefully that paper will come out soon. It's just an absolute tour de force computationally from Marissa's lab, and really beautiful work there.
Nice, very nice. Well, I think we're at the end of time, but I want to thank Mary and Caroline again for great talks. I think also plug these events, like, it looks like some pretty awesome people speaking. So, go check them out, and we'll see everybody hopefully a little later this year for our next virtual symposium.
Yep.
Take care.
Thank you, everybody. Nice job.
Thanks, everybody.